We've defined what K is. Now let's show what it is we can do with it. One of the things is we can look at the magnitude. How big is it? K could be much, much greater than 1. K could be much, much less than 1, or K could be just about equal to 1. Well, when we look at the numbers, I'm just going to focus on this first. K is much, much greater than 1. Here I have an equilibrium constant listed, and you see its exponent is 10 to the 38th. That tells us that the equilibrium lies to the right. It tells us that products are favored. It tells us the overall concentration of products is greater than that of the reactants. So what it says is if I have a gold cation and I drop in some cyanide anion, I will make a gold cyanide complex, and we will learn in chapter 17 that this is called a KF, and we will learn that it is very stable as we learn about thermodynamics because its K is much, much greater than 1. It's primarily products. If now, on the other hand, I have a K that is much, much less than 1, we can say equilibrium lies to the left, we can say reactants are favored, and we can say concentration of reactants is greater than products. Well, let's look at the example given here. It's an aluminum fluoride complex. It's an aqueous solution, and it could, because it is an equilibrium, break down to make the cation and the anions. But when I look at the equilibrium constant, it's on the order of 10 to the minus 30. That says that I am primarily going to have the complex. In the first example, well, they both are complexes, but you have to look at it and you have to think about it. The third case, I really don't know of an example to give you when Kc is about 1, when the forward and reverse reactions are equal, but practice. You can hear me talk, but you have to try it. Another thing to think about with K is what about the direction the reaction is going? And again, we've never really done this before. Here are the rules. We can be given a chemical equation. I'll label it 1. It's the one we had earlier. And someone could have gone in the lab and measured the K. What if we decided to reverse this reaction? And when I say reverse, you can see equation 2 sitting there. How can we find the K? Well, it says 1 over K. We will take the K from equation 1 and we will just invert it. What you need to notice is that the K's may be different, but both of them are going to favor N2O4. And that's essentially the kind of question you're going to be asked on a midterm. They will assume you know this information. They will be asking you to apply this information. So that's called direction. How is the reaction written? Another one that kind of breaks the rules of everything you learned in 1210. We could be given a chemical equation, and we could take that equation and we could multiply it by 2. And that'll be the equation that you see listed below. Well, what are you going to do to look at the equilibrium constant? What we did is here we multiplied. So we will take our K, and what we will do is we will raise it to the exponent, which is what we multiplied by. Because sometimes you multiply by 2 or by 3, sometimes 4, it really depends. But the whole idea is you do an exponent. So what we did here is we took our K1 and we squared it in order to get our K2. If we were instead to divide, and let's say we would divide by 2, what we would do is we would take the square root of K. Again, all the rules to follow. So the next one, the third one, the last one, is the temperature effect. And you may just say, well, if I heat something up, I'm going to get more product. But it has to be a case by case, okay? So what they gave you here is 1 kp at 298 and a second kp at 700. And the question asked is the formation of HI, the product, favored more at low T or high T? Well, at low T, there's a larger Kp, and that's the one that's going to favor HI. So this is what we're teaching at this point. But as we go deeper into the chapter, we'll talk about Le Chatelier. I'm going to add in something that I know. If I'm going to add heat, I am going to see a shift to the left. And that's essentially what happens when I increase the temperature to 700 K. I'm adding heat to this equilibrium. The reaction will shift and it will come back to equilibrium. Again, this is later, this is now. Going a little further. You really need to do the sample exercises. Maybe you didn't do a single one in 1210 and things turned out fine. This is sample exercise 15.4, practice exercise 2, and it's asking you to determine the value of Kp for this equation. They are going to give you two separate equations. What you need to do is manipulate them. If you had me for 1210, we talked about this in chapter 5 on enthalpies. So here we have two given equations. It's by trial and error. You look for something that only appears once. My eye is immediately drawn to the ammonia, and I see it here in this second equation. I need to make it a reactant, so I will reverse this equation, okay? If I reverse this equation, I have to invert the K. I have to go 1 over Kp for that second equation. So then my eye said, well, what should I look for next? Well, what I do is I see the Hi. I notice that it is in the first equation, but what I'm going to have to do is multiply it by 3. So, okay, I say times 3, but that means raise k to the third power. So I need to take k1 and cube it. So my k new comes out to be that k1 cubed, and it's the reciprocal of 1 over k2. There can be all kinds of manipulations. You need to practice so that you are prepared. The whole idea is we're given two separate equations. If we add them together, we need to manipulate the k's, and it's not, if nothing changed, we could just multiply them. But notice we had a multiplication and we had to reverse it. So those have to be carried out. We'll use this in the thermodynamics chapter. It's not a dead end here, it's just teaching you skill. I combine two things because heterogeneous equilibrium is very short. In 1210, we learned homogeneous was one phase. We learned heterogeneous was different phases. I'll take more time in the lecture Zoom, but I'll just run through it here. If I have a pure solid or a pure liquid, they have an activity equals 1 because their density is constant. I'll explain that in lecture Zoom. It's all based on the thermodynamic activity A. If I have an aqueous solution, any concentration, it is as if I have that concentration divided by 1 molar. If I have some kind of pressure, it would be that pressure divided by 1 atmosphere. Just have to accept it at this point, okay? More in lecture Zoom. So I give two examples. The first one is with lead chloride breaking down to form lead cation and chloride anion. I do not include the solid. And as you look at the K, there is the expression, there is no lead chloride in it. My second example, there's a little bit more built into this than meets the eye. If I want to write an equilibrium expression, no solid, no solid. Calcium carbonate to calcium oxide and CO2. The only thing that matters is the pressure of CO2. So I made even another slide for this one. If I have a given or a set temperature, the equilibrium pressure of CO2 is the same no matter how much solid is present. Now that just sounds weird, doesn't it? Here is the equation, took it out of your textbook, and again, my K, which is actually a Kp, is the pressure of CO2. So they show a picture. Large amount of CaO and small amount of, large amount of CaCO3, small amount of CO, or we could have a small amount of calcium carbonate and a large amount of CaO. We're going to have the exact same pressure. Now, the thing to make sure is you see the words that this is a closed system. Equilibrium constants only hold for closed systems, and this is a special case where the solids are not part of the equilibrium expression.